All right, let's jump right in. Today, we're taking a little road trip through a really powerful idea in mathematical analysis, uniform convergence. Now I know, it sounds super technical, but trust me, stick with me on this, because it solves a genuinely fascinating problem.
And that whole problem really starts with this one question. What if you had a whole bunch of perfectly smooth, continuous curves, one after another, and somehow they all converged to a curve with a glitch? You know, a sharp corner, or a break, or a total discontinuity. It just feels like that shouldn't happen, right? Well, it can.
And that brings us to our first stop, what I'm calling the convergence glitch. We're about to see why the most obvious, the most intuitive way of thinking about functions getting closer can sometimes go sideways and lead to some really surprising and kind of problematic results.
I mean, think about it. The obvious way for a bunch of functions to converge is just to check each point one by one. You'd say, okay, at x equals 1, are the values getting closer? Yep. What about x equals 2? Yep. And you do that for every single point. It seems totally logical. But this point-by-point approach, it has a hidden and pretty fatal flaw.
So this really lays out the two big ideas head-to-head. Over on the left, you have pointwise convergence. That's our glitch. You can picture each point on the curve just moving toward its final destination on its own schedule at its own speed. It's that total lack of coordination that lets important things like continuity just snap. But on the right, we've got the fix, uniform convergence. Here, the entire function moves as a team, converging at the same rate everywhere. It's just a much stronger, more disciplined way for things to come together, and it keeps all those essential properties safe.
So that leads us right into our second section. We need to get a better handle on this fix, this much stronger kind of convergence.
So what is uniform convergence, really? Well, it just means that the speed of convergence is the same across the entire function, and this slide has the perfect way to picture it. Imagine your final target function. Uniform convergence is like being able to draw a tube around it. And as you shrink the radius of that tube, eventually, the entire graph of every later function in the sequence gets trapped completely inside. They all have to fit all at once.
Okay, that's a great mental image, but in analysis, we need to prove things. How can we actually be sure a series of functions converges uniformly without having to check every single point forever? Well, luckily, there's a really clever tool for this. Let's introduce the analyst's absolute favorite shortcut.
The Weierstrass M-test. And this test is just a brilliant piece of simplification. Instead of having to wrestle with this complex, infinite series of functions, it boils the whole problem down to 3 simple steps. First, for each function, you just find a single number, m sub n, that's bigger than the function is anywhere, an upper bound. Second, you make a whole new series just out of those numbers. And third, this is the magic part. If that simple series of numbers converges, then you are guaranteed that your original complicated series of functions converges uniformly. It's an unbelievably powerful and practical tool.
Okay, so we found the glitch and we found a powerful test to fix it. But what's the big payoff? I mean, why do we care so much about this? Well, that brings us to section 3, the analyst's superpowers.
Because uniform convergence is not just some fussy technical detail that only mathematicians need to worry about. No, it is literally the key that unlocks 2 of the most powerful, most essential moves in the entire playbook of analysis.
And here they are, the big rewards. Uniform convergence gives you the green light to swap the order of limits with other operations. You can take the integral of a limit or the limit of an integral. You can differentiate a limit or take the limit of a derivative. Now that might sound subtle, but being able to do that reliably is pretty much what makes calculus work when you're dealing with infinite series. As you can see in section 5.3 of the source material, this is the bedrock for so many advanced calculations. This quote just nails it. This is the engine that makes much of modern analysis work. It ensures our mathematical machinery behaves as we expect. I mean, think about that. Without the guarantee of uniform convergence, a ton of the tools that we rely on in calculus and physics would just become totally unreliable. It's the safety check that makes sure the whole machine runs smoothly.
So, now that we have this incredibly powerful engine, what can we actually build with it? Well, that leads us to one of the most beautiful applications of all, which we'll look at in section 4, building with polynomials.
And as you can see right from the table of contents for chapter 5, these ideas of pointwise and uniform convergence, they're not the end of the story. They're just the beginning. They are the absolute foundation for a whole bunch of powerful theorems that come next. And one of the crown jewels that's built on that foundation is the Stone-Weierstrass Theorem. And what it tells us is pretty profound. You can take
any continuous function. I don't care how complicated or wiggly it is. This theorem guarantees that you can find a simple polynomial that gets as close as you could ever want to that function. And it's uniform convergence that makes sure that approximation is rock solid across the entire function.
Being able to approximate any function with simple polynomials is already a game changer, but the applications don't stop there. And that brings us to our final section, a quick peek at what lies beyond the limit.
You see, uniform convergence just opens up this whole new toolkit for doing analysis. It leads to really advanced stuff like the Arzela-Ascoli Theorem, which helps us make sense of entire families of functions. But maybe the most common place you'll see it in action is with power series. You know, those infinite polynomials that are basically the backbone of modern physics and engineering. Uniform convergence is exactly what gives us the confidence to differentiate and integrate those series term by term, which is what makes them so incredibly useful.
When you step back, each of these ideas, from the M-test all the way to the Stone-Weierstrass Theorem, it's really a step forward in our big quest to sort of tame infinity. They give us the solid, rigorous framework that we need to really understand and work with the behavior of functions in a predictable way.
The whole journey we just took really says something about how math works, doesn't it? We start with an intuitive idea, we find a problem with it, and then we build something stronger and more robust to fix it. And it kind of leaves us with this one fascinating final thought. If a concept as basic as getting closer can be refined and strengthened like this, what other mathematical rules that we just take for granted are not nearly as set in stone as they seem? What else is out there, just waiting to be rewritten?